We're going to continue with redox here. Did we finish the acid base? All right, so sometimes we got to look for redox reactions. And, let's take a look at some common types of redox here. The first type of redox is like a combination. You take two elements, A and X, and then you form AX. And so an example, did we do sodium and chlorine last time? Sodium and chlorine to form sodium chloride. You could also do the reverse reaction. You can take a compound and break it down into elements. So sometimes you could just heat it up and it'll break it down into elements. Other times you have to do something special to it. For example, water. We take the compound water, H2O, then we can decompose this into the elements, hydrogen and oxygen. The way we do this is electrolysis. So it's just providing a voltage and a current through water. You can electrolyze water. To balance this, we'll need two waters. We're going to form two hydrogens and one oxygen. The water is going to be liquid. The hydrogen and oxygen will be gases. The reverse reaction is also very favorable. The reverse reaction, this is decomposition, which requires electrolysis. This is combination. This combination is what we call spontaneous. Spontaneous just means it happens. There's a pretty big driving force for this. This one, the reverse is non-spontaneous, which is the decomposition of water. Non-spontaneous decomposition. In this case, sometimes decomposition is spontaneous if you have an unstable compound. Other times, combination. And so it goes both ways. One way is decomposition, the other way is combination. So this is what we have here. And so you can see it. One way we form AX, the other way we break AX back into the element. But we can figure out the compounds that we form typically. Like there's unless there's variable charge. So for example, iron and oxygen, two gas, can form different products. And so if we take iron solid and oxygen, well, we can form FeO, which is called, what would FeO be? FeO would be iron 2 oxide, or we could form Fe2O3, which is iron 3 oxide. And it depends on the conditions. Depending on the conditions, we form one or the other. Because iron forms +2, +3. So it could either lose 2 electrons to oxygen or it could lose 3 electrons to oxygen. These are redox reactions here. Redox reactions are electron transfer. Acid-base reactions are proton transfer. So we're looking at transferring electrons from iron, which is the reducing agent, to oxygen, which is the oxidizing agent. And so the reducing agent we abbreviate RA. This just stands for reducing agent. I'd written this up earlier. I'll write it here. OA stands for the oxidizing agent. And so we can figure out what the formulas for the compounds are, the products are, just based on the charges. What charges off the periodic table like to form. So this is an element plus element combination reaction. There are other forms. So this redox, a element and element. Basically forms compounds. So it goes both ways. Combination, decomposition. Another pattern that we see is something called the single replacement pattern. advantage is this simple pattern. Disadvantage is that one, you might miss reactions. You know, it's limited. It doesn't always work. What do I mean by work? Work is it doesn't always predict the correct reaction. Meaning it doesn't predict the correct product. All right, so basically your book is going to say it's going to be an element plus an ionic compound or acid. This is the single replacement form. And so it's A plus BX. A plus BX yields AX plus B. This is the pattern here. And so sometimes it works quite well. An example where it works quite well is magnesium. If we take magnesium, the element, so that's A plus HCl, it's our B. And then what would we predict? Magnesium chloride and hydrogen. So magnesium chloride would be magnesium 2 plus, MgCl2. And then hydrogen's a diatomic, so we're going to do diatomic here. So we get magnesium chloride and hydrogen. And then what we have to do is we have to balance this. We don't care about balancing it here, we just want the correct formulas. So we're going to need 2 HCl's. If we have 2 HCl's, then it's balanced. Then we write in the states. Chlorides are all soluble except for silver, lead, mercury. Hydrogen's a gas. So we have that. Now for redox, the driving force is different for redox. The driving force for redox is this. There's a simple one. You could use the activity series. So let's take a look at the activity series. This is the activity series here. If you look at the activity series, you might notice something about it. If you look at the activity series here, lithium, potassium, barium, strontium, calcium, sodium. What do you notice? I mean, does that sound familiar? Lithium, potassium, barium, calcium, strontium. Where did you see that before?
I noticed that those are some of like the strong bases.
Not the strong bases. Not the strong bases. Another chart. The strong. Well, they're group 1 and group 2, but you've seen that pattern before. Strong reducers. This is a strong reducer. If you compare this pattern to the one from here, lithium, potassium, calcium, sodium, magnesium, aluminum. Look at that pattern there. Compare it to this here. hydrogen and barium is running there. The lithium, potassium, calcium, sodium, magnesium. You see it's the same. And so at the top of this list, at the top of the activity series is the strongest reducer. The strongest reducer. Now, that's called the most active element. The most active element. And so the activity can be defined in two ways. Activity can be defined as a powerful reducer, or activity can be defined as a powerful oxidizer. It's actually both. But in the context of the activity series, we're looking at the reducing activity. So lithium is the most active, so it's the most powerful reducer. At the bottom of the activity series is gold. Gold is the least active on this platinum gold here. And so basically it's this. The activity series is, how easy is it to take electrons? Lithium is the easiest to take electrons from. Gold is the most difficult. And so in other words, how easy is it to oxidize these? So lithium is very easy to oxidize. In fact, lithium is so easy to oxidize, they give you a little descriptive visualization here. It will replace hydrogen from liquid water, steam, or acid. In other words, the way people typically remember these is these metals here are so reactive, they'll react with water, liquid water. In other words, do you think of liquid water as being a powerful oxidizer? No, you don't really think of water as being an oxidizer. If you have a cup of water, do you start taking antioxidants because you don't want any oxidative damage? No, you don't do that. And so let's compare it to ours. So where is water as an oxidizer? Well, water seems to be at the bottom of the oxidizing list, but it's truly not at the bottom. Does anybody remember where water belongs? I mentioned this a long time ago, where water belongs. It's not at the bottom. It's because these are separated into two separate tables. Water is a stronger oxidizer than what, and a weaker oxidizer than what? Doesn't ring a bell at all. You said a long time ago, so this is a long time ago. But water is a stronger oxidizer than aluminum 3+, and a weaker oxidizer than Zn 2+. This is what this triple dash line means here. Surface water there. So that's where water belongs. Water belongs here. How did I know? It's based on this number, minus 0.828. Where does minus 0.828 fall? It falls between minus 0.763 and minus 1.6. And so between those two numbers, we insert water. This is what I did here. This is what you should write a note. But water belongs there, so it's it's not the worst oxidizer, but it's certainly not very good. It's better than aluminum 3+, but worse than Zn 2+. And so what can water oxidize? If water is here, then we need a reducer that's more powerful than hydrogen and hydroxide. So what's a reducer more powerful than hydrogen and hydroxide? Zinc? No. Anything below it. So aluminum, magnesium, sodium, calcium, potassium, lithium. And so water is capable of reacting with all these here. Now how does it react with those there? And so let's take a look at this. Well, we don't even have to know that because it's not necessary to know, but it's necessary to know something like sodium. Sodium is a very active metal. It's so active it can react with water, which is an extremely weak oxidizer. And what forms? Well, in single replacement form, the way we treat water is HOH. And And so in single replacement form, this would be our A, this would be our B, this would be our X here. So that's our ABX. And so what forms here? It would be sodium with the hydroxide, so sodium hydroxide plus, and now B is just going to be H2. So we'll need to balance this out here. So how can I balance it? Well, I have the sodiums are balanced. I have one sodium, but over here I have two hydrogens. I have three hydrogens. That's not quite bad. Okay, if I put two there and two here, now will it balance? So I've got two sodiums. I just have two hydrogens, but I have four hydrogens. I need two front of water. So now that gives me four hydrogen atoms, two oxygens. Now it's balanced. Now, there's two ways that you could say there's a driving force. One way is we could do it off this, this chart here. See, it's favorable reaction based on the chart. The second way we could show this is by comparing the activities of the two elements. When we compare the activities of the two elements, we're comparing A to B, A versus B on the activity series. And so the activity series is to compare A and B. What we want to do is we want to go from more active to less active. And so we got to look at which one's more active. Is the sodium metal more active or hydrogen gas more active? And so let's go back to the activity series here on the chart. Sodium metal versus hydrogen gas. It looks like sodium is a lot more active. In other words, it's a lot less stable. It's much more reactive than hydrogen. And so in this case, this turns out to be more active. This is less active. And we call this driving force. So basically what we're doing is we're going from less stable, more active, more reactive, to more stable, less active, less reactive. So that's it. Okay, this only works for single replacement because for these single replacement we only have the activity period. But for all redox reactions, we have the same driving force. For all redox, we have the same driving force. The same driving force is this. We're going from a stronger oxidizing agent and a stronger reducing agent to a weaker oxidizing agent and weaker reducing agent. And so this is the general driving force for any redox reaction.
For sodium, you would say it's a strong reducer.
Yeah.
And a weak oxidizer?
No. For single replacement, this is the pattern. For single replacement, it fixes the roles. This is why it fails. For single replacement, it assumes some things. Assumes that A is a reducing agent, and then B is your oxidizing agent. X is the spectator. And then when we go to this side, we're going to form AX plus B. And so what we think about is we have a competition. We have the forward reaction competing with the reverse reaction. If we're to go backwards here, then B is our reducing agent, and A is our oxidizing agent, and X is the spectator again. And so a chemical reaction is a competition between the forward and the reverse. You know, as we form products, the products themselves react. And so when we look at the activity series is sodium is a stronger reducing agent, right? Start it over here. And we end up with sodium is a stronger reducing agent. Then hydrogen is a weaker reducing agent. So all we need is one, you know, we're going from stronger reducing agent to weaker reducing agent. Sodium's a stronger reducing agent, hydrogen's a weaker reducing agent. How about the oxidizing agents? The oxidizing agents in this case are going to be, well, the oxidizing agent here is going to be H+. That's our oxidizing agent. The oxidizing agent here is going to be sodium plus. So which one is a stronger oxidizing agent? H plus or sodium plus? Well, that's not on the activities chart, because the activity chart just looks at the producing agent. It just looks at 1/2. But all you need is 1/2 because of the conjugate relationship. If the oxidizing agents follow, then the reducing agents must follow. If the reducing agents follow, then the oxidizing agents must follow. And so they have to go hand in hand. And so you only need to look at one, either the reducing agents or the oxidizing agents. And in the activity series, they figured the easiest is just to look at the reducing agent. But in general, it's easier to look at the oxidizing agent for general redox. That's just. But anyway, which one's a more powerful oxidizing agent? H plus, which is here, or sodium ion. So here's H plus. Let's figure out what sodium ion is. Sodium ion's way down here. It's not a good oxidizer, so you know, HCl is a decent oxidizer, but sodium chloride. Is sodium chloride a good oxidizer? HCl can eat up magnesium. Actually, HCl. Well, anyway, this is not HCl. This is the H plus in water. So I have to put this in quotation marks because water is not hydrogen hydroxide, really. But we're just treating it as such in a single replacement reaction. So this is how we can see, you know, all these metals down here are going to be attacked by water, including aluminum. But our experience with aluminum is that it's not attacked. You know, if you have aluminum at home, is aluminum reacting with the water to form hydrogen gas and aluminum hydroxide? No. And the reason aluminum doesn't react, does anybody know why aluminum doesn't react with water? Because, like, for example, this is aluminum here. The reason why aluminum doesn't react is because it forms a hard barrier. The hard barrier is aluminum oxide. And so there's aluminum oxide that coats this, and the aluminum oxide is pretty much an impermeable film. That is, it forms a nice, complete coating on there. Whereas rust is very porous. And so rust does not protect the underlying iron, whereas aluminum oxide will. And so what a lot of people do is they try to generate an oxide, a thick coating of oxide on aluminum to protect it. That's called anodizing aluminum. Put a thick coating. Whereas you can't anodize iron, because if you did that, you're going to form rust, which peels and flakes off, and you'll get continued corrosion. So aluminum's special. But if you remove this coating, then yeah, it'll react. It doesn't react very quickly, but it'll react slowly. Because it's not that, it's almost the same. So this is the activity series. But in general, this is, for all redox, we're looking for stronger to weaker. And precipitation, gas formation, doesn't matter at all. It doesn't matter that we're forming gas. It doesn't matter that we're forming precipitate. So let's look at an example here. Precipitation, gas formation are not driving forces for redox. So an example of this would be like this reaction that we saw earlier. H2O liquid is going to form 2H2 gas plus O2 gas. So here we're forming lots of gas. Lots of gas generated. And so will a cup of water decompose into hydrogen gas and oxygen gas if you just leave it on your kitchen table? A cup of water, a glass of water? Not at all. That means, it's not a driving force. Let's try another one. Try this one, hydrogen gas plus sodium chloride. What do you think you're going to form here? We take hydrogen gas plus sodium chloride. Well, we're going to do this by a single replacement, A plus Bx, style pattern. So if I bubble hydrogen gas through salt water, just follow the pattern. A plus Bx yields Ax plus B. So A plus Bx yields Ax plus B. Ax would be what? HCl. And B would be Na, solid. Liquids. So we got precipitation here. Is it a driving force? The answer is no. Why? Because this is redox. Redox doesn't care if you form a precipitate. Redox doesn't care if you form a gas. The reason redox doesn't care is because the changes in the oxidation state leads to huge changes in energy. Whereas in metathesis and acid base, there's no changes in oxidation state. In other words, is there a driving force here? We can't tell based on the precipitation form. So if we bubble hydrogen through salt water, are we going to expect a precipitate of sodium metal to form? The answer is no, because we look for going from stronger to weaker oxidizer reducers. Or in this case, since this fits the single replacement form, we just look at activity. What are we comparing the activity of? Hydrogen and sodium. So let's compare the activity of hydrogen and sodium. We'll use our chart here rather than activity chart. Here's hydrogen. Here's sodium. Which one's more active? Lithium being the most active. Sodium. And so there's no reaction that should occur here because this is more active this is less active. And so we're going from less active to more active. That's not stable. So NR. Let me qualify this. NR for single replacement. NR for single replacement. All right, so what we're going to do is we're going to look at some single replacement reactions. Here. And so all these can be oxidized by water. All these can be oxidized by water. So water's here. So water being an oxidizer can oxidize any reducer stronger than hydrogen. So it's all these. But can it oxidize zinc? Will water oxidize zinc? Iron? No. These ones will not be oxidized by water. However, these ones can be oxidized by H+. You know what we call H+? We call it acid, mineral acid. And so H+ is capable of oxidizing everything below hydrogen. And so acid can oxidize all these. All these metals are called the active metals because the active metals can be oxidized by mineral acid. But can H+ oxidize copper? H+ oxidize copper? No. Now I have to qualify this because it depends on the conditions. You know, you change the conditions. For example, you make it more or less concentrated, you know, or you make it hotter or colder. That changes how things react, you know. And so, of course, if you make it hotter, you can make things more reactive or less reactive. More reactive. And so if you use hot water or even steam, that could change the reactivity. And so we see that here. You don't have to memorize this because we're going to just look at normal conditions. Under normal conditions, water can oxidize these. Under normal conditions, water cannot oxidize these. Normal conditions, but acid can. Acid's H+, and so acid can oxidize everything all the way here, right? However, under abnormal conditions like steam can actually increase its oxidative ability and become more reactive. So steam can actually oxidize these here, but it won't oxidize these. It's just acid. But it also depends on the temperature of the steam. You know, steam can get very hot. It's not just 100 degrees, it can be well above 100 degrees. And so superheated steam probably will oxidize these as well. It depends on the conditions. And so normally when I think about this, I just think about normal conditions. Now, what are normal conditions? Normal conditions are room temperature, which we call 25 degrees C. And it's the concentration. It's at a concentration of 1 mole of substance in a liter. And so that would be the concentration here. We'd have 1 mole of acid in a liter of acid solution. We call that 1 molar, which we'll talk about later. However, if I use concentrated acid, let's say rather than 1 mole, if I use 16 moles of acid and put that into a liter, that's a heck of a lot more concentrated. That's 16 times more concentrated. At 16 times the concentration, it's going to be much more reactive. And so it could change things. You know, it could cause things to react that don't normally react. And so of course, by altering the conditions, you can change the reactivity. But if we keep altering the conditions, then we have to have a huge database of knowledge memorized. It's too much to memorize, what happens at this temperature, what happens at that temperature, right? What happens at this concentration, what happens at that concentration. And so what we do is we normalize the conditions to normal conditions. This is called normal thermodynamic conditions. And then we memorize that. And then, of course, we think, what would happen? What if I increase the temperature? What if I increase the concentration? It should be more. What if I decrease the concentration? It should be less. And so this is our base here. This is how things react under normal conditions, but of course we can always alter the conditions, go abnormal, quote unquote, conditions, and then that can make things react differently. So we always keep that in the back of the mind. So steam is an abnormal condition, so you don't have to remember that. You just remember acid. And so acid will replace these. Now, acid is H+, so we need a reducing agent stronger than hydrogen, H+. But if we have a reducing agent weaker than hydrogen, like copper, there's no reaction. Silver, there's no reaction. Palladium, platinum, gold, no reaction. Mercury, antimony. Antimony's not that common. These metals are the inactive metals. The inactive metals, you need to oxidize are more powerful than H+. Are there oxidizers more powerful than H+? If you want to get copper to react, how could you do that? Well, we need something more than the activity series to figure it out. If I want to attack my copper, say I want to react it, I want to dissolve my copper chemically. What oxidizer can I use to oxidize copper metal? Can I use this? This is sulfate and H+. You know what sulfate and H+ make, that ion combination? Makes sulfuric acid. Will sulfuric acid dissolve my copper? Would hydrochloric acid dissolve my copper? Now, hydrochloric acid, I don't see hydrochloric acid here. But hydrochloric acid is here because the hydrochloric acid yields H+ and chloride. Right? Hydrochloric acid, HCl, yields H+ and chloride. Why didn't they include the chloride here? Why did they include sulfate for sulfuric acid? Because H+ and sulfate make sulfuric acid. Why did they include it here? Because I have plenty of H+. In fact, I have more H+ than I need, but I need those additional H+ to form water. But why do I have the sulfate here but not the chloride here? Because there's a huge difference in the anion. And so we have two types of acids, actually. We have mineral acids. Have you heard the term mineral acids? And we have oxidizing acids. Mineral acids have an anion that it's not an oxidizer. Chloride's a reducer. It's a very weak reducer. And so in a mineral acid, the only oxidizer present is H+. But sulfuric acid is what we call an oxidizing acid. It's an oxidizing acid because of this. When we look at sulfuric acid here, which would be a combination of H+ and sulfate, is the H+ taking electrons, like here, the H+ took 2 electrons to form hydrogen gas. Is the H+ taking electrons to form hydrogen gas there? No. What's taking electrons in sulfuric acid? What's taking electrons in sulfuric acid is not H+, it's not, there's no water here in the reactant. It's sulfate. Let's look at the oxidation states. What is the oxidation state of sulfur and sulfate? What's the charge on sulfur and sulfate? +6. 6+. What's the charge of sulfur and sulfur dioxide? +4. So we went from +6 to +4, which means we must have gained 2 electrons. And so the oxidizer is sulfate, which means that sulfate is a more powerful oxidizer than H+. It's, in other words, sulfate is more electron poor than H+. So it makes it more powerful. And so oxidizing acids, the anion of the oxidizing acid turns out to be more powerful than H+ alone. But we do need the H+. We need the H+ to form water. Take a look at this combination here. This is nitrate and H+. Nitrate and H+, what does that combination make? That combination makes HNO3. HNO3 is called nitric acid. Why is nitric acid way up here and hydrochloric acid way down here? Because nitric acid is what we call an oxidizing acid. It's not the H+ that's doing the oxidizing. What is it? It's the nitrate. Nitrate turns out to be a powerful oxidizer because it's quite electron poor. What is the oxidation state of nitrogen in nitrate? +5 is correct. And then what is the oxidation state of nitrogen and nitrogen monoxide? +2. So we're going from +5 to +2 by gaining 3 electrons. And so an oxidizing acid, the anion is the oxidizer. The anion is very, very strong. And so hydrochloric acid, interestingly enough, copper metal again, plus hydrochloric acid. This is the A plus BX, yields what? A plus BX, for those of you who like patterns, A plus BX yields AX plus B. That's easy. AX plus B. AX. Well, unfortunately, we have a choice here. We could go copper 1 chloride or copper 2 chloride. Which one should we go? Copper 1 or copper 2? Now, the answer is which one's more common? If I look at copper, did copper go to copper 1 or did copper go to copper 2? It went to copper 2. Is there copper 1 here? Did you see copper 1 here? There's no copper 1 here. So what do you think it goes to? Copper 2. We go to copper 2. So this is going to yield copper 2 chloride, which is going to have the formula Cu Cl2. Good. And then B is going to be what? Hydrogen. Copper 2 chloride is states here. And so we compare A versus B. A is copper, which is less active. B is hydrogen, which is more active. You know, what would you rather fill your trunk, the trunk of your car with? Hydrogen gas or copper metal? Copper metal, I mean, well, I don't know, but copper weighs a lot. Hydrogen doesn't weigh much. But yeah, if the hydrogen caught fire in the trunk, it would be very bad news. So anyway, so what do we predict? There's no driving force, right? So we predict NR, but we have to qualify it. NR for single replacement. Is it NR for redox? It turns out it is NR for redox too. Now, single replacement method fails, you can tell when it's going to work and you can tell when it's going to fail. Because what did we define these? What was A defined as? Single replacement works if A is the strongest reducer present. In inventory. And B is the strongest oxidizer in the inventory. It fails when it's not, because single replacement automatically makes the assumption that A is the reducer, B is the oxidizer, and X is the spectator. And so let's repeat this here. With rather than HCl, we're going to try HNO3. We get A plus BX. A plus BX yields AX plus B. So AX is going to be copper 2 nitrate, which is CuNO3 2. And B is going to be H2. Okay, again, this is going to be no reaction because this is less active. This is more active. And so we're going from less to more active, which means NR. But NR is wrong here. NR is wrong here because we're assuming something. Is copper the strongest reducer present? Well, what is our inventory? This is wrong. There is reaction. There is redox. I just wrote NR. I didn't write NR. If I said NR for single replacement, that'd be correct because single replacement makes a false assumption. And so the inventory here is this. What are all my species present? If I inventory, I have copper, I have H+, I have nitrate, and I have one more, which is always a tricky one. But what's my water? Water is always tricky because you don't really think about it being reactive. But remember, water can react. It's more stronger than Al3+ and weaker than Zn2+ as an oxidizer. What about as a reducer? You see it up here? As a reducer, water is stronger than manganese 2 but weaker than iodine as a reducer. And so water here can react. And so we have to account for that potential reaction. And so, what is copper? Copper is a reducing agent. It's on the lithium side of the. What is H+? An oxidizing agent. What is nitrate? Nitrate is an oxidizing agent in combination with H+. So if we have H+ and nitrate, that's good. What is water? Water occurs on both sides, so it's both an oxidizing agent and a reducing agent. Now, how many reducing agents do we have present in the inventory? 2. So which one is a better reducing agent? Water or copper? Well, let's pick the best reducing agents, lithium. Go down the list. Water's here. Did I pass copper? Yes. Copper's here. And so this is the best reducing agent. So this is the best. And so that's okay because single replacement assumes that A is the reducing agent. So that's valid. This is valid. Now, single replacement predicts that B is the strongest oxidizing agent present. Well, let's see. Is B the strongest oxidizing agent present? And so how many oxidizing agents do we have? We have 3. And so we'll start off with the best oxidizing agent, which is fluorine, and then work our way down. And the first oxidizing agent that we hit is nitrate. Well, single replacement says nitrate is not reactive. Single replacement says nitrate should be a spectator. But if nitrate is a more powerful oxidizing agent than H+, then is it going to be a spectator? No, it's not going to be a spectator. So this is single replacement assumes this is the strongest. That's wrong. It's wrong. It turns out that this is the strongest. This is the strongest. So what that means is, of course, we're going to get the wrong answer. If we use the single replacement form for this, we're going to get the wrong answer. There's a reaction that occurs. Another reaction that occurs. Another potential reaction. Okay, so this is failure 1 for single replacement. Fail. Here's another one where single replacement fails. Another one that single replacement fails is going to be this. Let's bring up the other chart here. I didn't have nitric acid wasn't on that, but this one will make this chart here. I'm going to go with sodium metal plus potassium chloride, AQ. Okay, so if we do the A plus BX pattern, the A plus BX pattern is what? This is going to yield AX plus B, which is going to be sodium chloride plus potassium. So let's compare A versus B. A versus B, which one's more active? Well, looks like potassium is more active than sodium. See that? So this is more active. This is less active. So if we're going from less active to more active, there should be no reaction. NR. But NR is wrong. There is reaction here. In fact, this is a very dangerous reaction. You never want to do this because you're going to cause an explosion. And so, what am I missing? Well, isn't it precipitate? Shouldn't there, look it, I'm precipitating on potassium metal. If I precipitate on potassium metal, isn't that a driving force? Not for redox. Does redox care if you form a precipitate? No. Redox doesn't care. It's not wrong because of the precipitate here. It's wrong because of something else. Can you figure out why this is wrong? Single replacement made the wrong assumption. And so the inventory of reactants here, I don't look at the product because we're just mixing sodium and potassium chloride. And so the inventory is going to be sodium, solid, potassium ions, AQ, and chloride ions, AQ. Am I missing anything? I'm missing water. And single replacement is going to tell me which one is the best reducing agent. Well, what are my reducing agents present? I have sodium. I have to go to my other chart. Okay, because the reducing agents are going to be on the lithium side of the chart. So, the lithium side. So sodium is a reducing agent. How about potassium ion? Now, this is potassium metal. Do I have potassium metal or do I have potassium ion? Remember, this is like Dr. Jekyll and Mr. Hyde. I don't have potassium metal, I have potassium ion, which means that this is on the fluorine side, which is oxidizing. And then I have chloride. Well, what is that? Is that Dr. Jekyll or Mr. Hyde? And so I would go up here and look. Chloride is going to be electron rich or electron poor in this sense. Yeah, compared to chlorine. Chloride is reducing agent. And then water is both an oxidizing agent and reducing agent because it occurs on both sides of the chart. And so which one is the strongest reducing agent? Chloride?
We have a single replacement assumes sodium is the strongest.
Yeah, single replacement assumes sodium is the strongest reducing agent. Is it? Well, what's the strongest reducing agent on the chart? Lithium. And it looks like sodium is indeed the strongest. So single replacement got that right. This is the strongest here. So it got the strongest. That's correct. Sodium is the strongest. But is potassium ion the strongest oxidizer? Did single replacement get that right? So let's take a look at the oxidizers. Well, you can already see where potassium ion is. Do you see where potassium ion is? It's at the bottom. Well, is it really at the bottom? Isn't water at the bottom of the list? No. Water is not at the bottom of the list. Actually, water is where? Yeah, at the triple bar here. I should have made this more prominent, but I didn't want to make it too obvious. But I should have made it too obvious. I don't know, but it's your job to make it obvious, right? And so H2O belongs here, which means H2O is the stronger oxidizer than potassium ion. Did single replacement even consider H2O? No. Single replacement didn't even consider H2O. This is a trick. The reaction is not going to be between sodium and potassium chloride. The reaction is going to be between sodium and water. And that's going to be a very violent reaction. Remember Lake Lenore in Washington? This is why I say if you ever did this, you might think there's no reaction based on single replacement, but you're going to have a huge explosion if you ever tried this. One more fail I want to show you. These are the three most common fails. Do chlorine plus sodium bromide here. This is going to be A, my element A plus Bx. This is going to yield what? X plus B, which is going to be chlorine bromide and sodium. Chlorine bromide is a weird one. That's our AX. And so we compare this and we say, okay, we're going from A to B, which means we're going from, well, which one's more active? Chlorine or sodium? Yeah, according to the chart, sodium. Where's chlorine? Is chlorine here? No, chlorine's not here. Because I'm comparing two reducers. And so chlorine's going to be up there somewhere off the chart. It's not here. Because that's it. But if I were to use this, and then switch sides, can you switch sides? Because here we're comparing sodium with potassium. They're on the same side, right? We can't switch sides because single replacement is assuming we're comparing active reducers. We're not comparing the active reducer with the active oxidizer. And so that's one fail. But even if we did this, we'd expect, okay, no reaction, because we might say sodium is more active. Let's just say that. We expect no reaction, but indeed there is a reaction here. So that's wrong. There's a reaction here. And so if we break this down, let's inventory this. If we inventory, we've got chlorine, we have sodium ions, we have bromide ions, and we have water. So single replacement assumes that chlorine is the best reducer present. Does chlorine want to give up electrons? No, in fact, when we look at the chart, chlorine doesn't even occur on the reducer side. Chlorine is not a reducer. Chlorine is a oxidizer. And so immediately that's a huge fail, because single replacement is going to call chlorine a reducer. It's not a reducer. Chlorine's a oxidizer. Sodium ions, oxidizer. Bromide, reducer. Water, oxidizer or reducer. Bromide occurs on the reducer side. And so what is the best reducer present? Here, it's not chlorine. The best reducer present is, here's bromide. Where's water? Here's water. So bromide versus water, which one's better? Bromide. So bromide, single replacement predicted that to be a spectator, but it turns out that's the best reducer present. Single replacement predicted A to be a reducer, but which is the best oxidizer present? The best oxidizer present is fluorine's the best. Fluorine's the best, and then chlorine, and then water and sodium. Water is next here at the triple line, and then sodium is down here. Sodium's the worst. And so, single replacement predicts sodium ion, the worst oxidizer present here, to be the best oxidizer. That's wrong. The best oxidizer is chlorine, so it's got it all mixed up. So you can see, obviously, single replacement is going to fail. And so what that means is, if you're going to memorize the A plus BX pattern, you have to memorize at least 3 more patterns. You want to memorize 3 more patterns? Okay. So what do you do? Well, our book doesn't have you memorize 3 more patterns minimum. You know what our book does? Our book says, okay, rather than open up the playground, so you could go to the big kids playground, we'll keep you in the little kids playground. In the little kids playground, we are not going to have those things come in. And so you don't have these types of reactions to screw your predictions up, right? But the problem is once you go to work, are you going to be working in the little kids playground or in the big kids? You're going to be working in the big kids playground, right? And so once you go into work, this is artificially limited. We're going to say, okay, we're just, in the homework, we're not going to give you these kinds of reactions that could potentially mess up your predictions. We're going to just give you things that work. But is that the way you want to learn it? Not unless you know what's out there, right? But if you go in with a misconception that you got it covered, you don't have it covered, right? And so what we're going to do is we're going to do this. So warning signs. Single replacement's great because it's so easy. A plus BX equals AX plus B. Compare it on the activity series. It's so easy. the warning signs are this. Okay, use single replacement. But, you know, watch out. Watch out for one. What was the first one that we covered? The first fail. I called it, take a look and see if it's in your notes.
You call it something?
I called it something. Acids. I had two types of acids. What were mineral acids and oxidizing acids? And so watch out for oxidizing acids. Oxidizing acids mean that it could fail. What are the oxidizing acids? The oxidizing acids are going to have an anion that's electron poor. And so the oxidizing acids would be HNO3, that's one. HClO4. Perchloric acid is a powerful oxidizing acid because perchlorate is unhappy. HClO3, chloric acid even. Chlorous acid, well, that's not as bad, or hypochlorous acid. Hypochlorous is bad. Hypochlorous is more mineral acid-like. These types, etc. And so when you see an anion that's electron poor, and you can tell it's electron poor by, you know, it's got a lot of oxygens there, whatever, then watch out. Versus HCl. Is chloride electron poor? Is chloride a powerful oxidizer? No. Versus acetic acid. Acetic acid, these are mineral acids. Mineral acids, it's only H+. Oxidizing acids, it's X. X is the powerful one. Here, it's just A, B, which is H+, which was B. So these are mineral acids here. So if we have an oxidizing acid, it's likely that single replacement is going to fail. What else do you have to watch out for? Water. Even though water, you know, water is not very reactive, right? But when you're dealing with aluminum, magnesium, sodium, calcium, potassium, lithium, watch out, right? What else do you need to watch out for water reacting with? So you got to watch out for water when dealing with these guys here. And you got to watch out for water when dealing with, well, where else do we see water? We see it on both sides of the chart. Here's water. You got to watch out for water when dealing with these guys up here. Water can potentially react. And so you got to watch out for water. Water can be an OA or an RA. And the third thing we got to watch out for, so it's only when we're dealing with extreme. Well, that's easy. You know, in Chem 4, we'll never deal with these. Easy enough. Don't deal with these. Don't deal with those. Then you're okay. You're safe. And it's easy not to deal with those because those are so reactive. Chemicals wise. This is a little bit more difficult not to deal with because nitric acid is a very common acid. Wow. And so this is more of a problem. And 3, what else do you watch out for? You watch out for when A is not a reducer, but A is actually a strong oxidizer. And so you got to watch out for elements that are oxidizers, elements that are oxidizers. And so, like for example, in Chem 1A, they might give you the X2 plus BY pattern, 2BY. The X2 plus 2BY pattern gives you 2BX plus Y2. And here we compare the oxidizing strength. Compare the oxidizing activity, not the reducing. You're not going to find these on the activity series. You have to go back to the other chart. You compare the oxidizing ability. Here, you'd have to memorize a pattern for each of these. Do you want to memorize a pattern for each of these? No. That's actually, I said 3 additional. You got to memorize a lot depending on how many oxidizing acids you have, and you got to have an individual pattern for each one because they form different products. And so very quickly, it's very beneficial. Single replacement is very beneficial if you know the limitations, and it works most of the time. So this is why I say it works most of the time, but not all the time. Actually, I forgot to break that. So what do we do? Okay, so I'm going to pause it here.